And we're
Okay.
next. Yeah, let me quickly introduce you. Here's the next talk for Meeting C++ 2025. This time is Hari Prasad Manoharan with binary parsing C++ 23 style. Looking forward to your talk. Please take it away.
Okay. So hello everyone. So my topic would be about parsing binary formats in C++ 23. So let's maybe introduce myself. So I'm Hari. I've been working in Ambition. We are a subsidiary of Mercedes, and we develop all the infotainment software in the current car lines. In my team, we are creating APIs for the application UI developers so that they can exchange data with the other ECUs, and we abstract away all the underlying communication protocols and also promote API reusability among car lines. And these are the handles where you can reach out to me if you're interested to collaborate with me. So maybe sort of little disclaimers. So I'm not an expert. I'm just a dude, and I've been writing C++ now for around 6 years. So uh, just sometimes you can take a few of my advices with a pinch of salt. And the views presented here in the presentation are not of my employer. The project is a personal pet project, and it grew up after that. But I did consider a lot of uh, feedbacks from my peers from my office and outside my office, right? And the project is not production ready, at least not yet. I plan to somehow finish this by early 2026, but it's still with the pet project label. And then we walk through a very simplified version of the project source. Why? Because the original source is close to 5,000 lines, and it wouldn't be practical to go through this in a single talk, right? And also, most metaprogramming talks are like magic, and so we have to cover as many basics as possible. So I chose a minimal version of the code, and then we skim through as much details as possible. This way, we also avoid this famous meme where someone teaches you to draw an owl, and then in the first slide you draw a couple of circles, and in the second you already end up with an owl, right? That's something we should avoid. So yes. How this project came to be. So parsing binary formats is something every developer will run into at some point of their life, right? When I started back in like say 9 years ago, so I have to parse some controller area network data, like the CAN bus data. So I have to like work with it and then parse them. Then I have to parse some binary formats like GIF files for my pet projects or ELF files in my production code. So at some point, everybody will have to do this. But the problem is there is no good declarative way to do this yet in C++. And you either have to do some evil macros or some code generation, too much of boilerplates, and none of them were like declarative to me. So and around this time I came across some projects and some talks online, and the first one was by Hana Toshikawa. It's about compile time regular expressions, and then I got to know about how to make sure how you can generate parsers at compile time using template metaprogramming. And then there were also other talks by Chris Josiak. So as I wanted to thank them, because without their projects we wouldn't have them, this small project. And as a side note, watch talks, attend conferences, meet people. It would definitely help you to grow your skill set, right? So that's how the project came to be. So if this would have been an on-site talk, I wanted to do a short quiz, but I'll stick to a fact check in the online version. So no trick question, but what would be the output? Like, let's say the hex dump at the bottom is a file we have from the disk, and then we try to read this in our code. And what would happen? In this case, we are lucky. It would work. It prints all the fields as expected because there is no alignment issues, there's no padding issues, and so on. And as soon as you say reduce the size, because your file format is in that form in that way, this would no longer work, because now the compiler adds some padding for the second member, and it starts taking the 4 complete bytes for the second member. So the output would not be what you expect. It might be undefined for each runs, maybe in worst case. Or maybe the format was trying to have some sort of an optimization. It wanted to only have 3 bytes for a field, but in the C++, there is no 3 byte data types, right? So you'll still have to stick with the 4-byte UN32, and still this reinterpret cast wouldn't work because it's still going to take the it's still that just doesn't fit the alignment and padding. So still problems. So what is the solution? The solution would be to do a reinterpret cast individually for each members. You'll have to roll everyone individually with right sizes, and then you would have the desired output. But I just cleaned it up just for some readability. I extracted into a separate function, write some clean context per members to denote the sizes, and everything is okay. Everything is fine. But then someone had thrown a illegal file to you. In this case, the file is truncated. Maybe the last few bytes are not there. Now we'll have to handle error case. In this scenario, it's like handling your buffer exhaustion, right? So modern C++ has std expected. So we can have either a value or an error with the std expected data type. So I just handle some basic error. In this case, we just handle the buffer exhaustion. And after a few months, we have a new data type. In this time, we have a member 3, which is optional UN32, but it depends on another field. In this case, member 2, and this member 3 would be present only if member 2 is equal to true. So you get the exercise. You'll have to go back to your code, copy paste once more, and then add a condition. So too much of boilerplate. So we'll have to have conditions like nested structs. Length prefix data types. You might have to have strings or vectors whose length is just before or somewhere else in your payload, and you'll have to parse a vector. Or you will have unions, like you can say my field's type and length depends upon another field. If it is A, then it is B, but if it was C, it was like something else. So the tag length value case. Or you'll have to handle different endianness, because binary formats can be either written in little endian or big endian, and there are also formats where the endianness depends upon a hint at the start of the file. I mean, this is also a use case. Then you might have to check, okay, I'm reading an integer, but in this binary format, I have an integer which should be within range A and B, but if it is not, I have to stop the passing right away. Or you might have delimited fields. For example, if you take a GIF files, and then you will have an array of records until the end of stream. So you want to say, okay, until end of stream, I have to parse something. Or you'll have magic numbers. Again, in GIF files, you have a magic GIF string at the top, like at the start of the file. So if you're a Marvel fan, so it's, as Dr. Stephen Strange would say, things just got out of hands, right? So yes. So what are the possible solutions we have here? We can depend on a domain-specific language. We can use something like HiTai, which I found online, which can be a custom DSL, and then you can follow this DSL to describe your data structure, and then this generator from the DSL package would then generate bindings for multiple languages. Or maybe you can't use open source software, you're stuck with some licensing issues, then you might have to be using your own DSL and your own code generator. The third option is an embedded DSL, like from using your own language. So in this case, you might have to depend on template metaprogramming to do some magic. Or there is a little surprise, a gift for everybody, which I'll come to the very end. And please make note of this. So I chose template metaprogramming because it's fun. I wanted to explore the depths of the language. And most importantly, it's also related to the little surprise I talked about in the previous slide. So why not do template metaprogramming magic? So the promise, what do I promise you? What does the library promise you? So it promises no macros. Yeah, macros are evil. Reasonably good error message. I mean, reasonable here, like especially in the compile times. Template metaprogramming has been it's been difficult to work with respect to compile time error messages. You get pages of errors, but at least with C++ 20 and above, with all the concepts, it's getting better. And also at runtime, like when you run the parser, and then you might have to know if your field really was parsed or not, what was the reason it failed, and so on and so forth. And the parser should be generated at compile time. And I have and there's a little example. I have marked a link to the godbolt. And then it has to be const expert as much as possible. Today, const expert everything is a trend. And here I would like to draw a little line. So yes, you could parse data structures at compile time with the library, but it is not the sole purpose of the library. The main purpose is to generate the parser itself, right? It is indeed possible to parse data structures at compile time. So, and there is also a link to godbolt. Maybe we can also look at it at the end of the talk. And we have to support for all the things Dr. Stange was talking about earlier. We'll have to validate the fields, especially while in place while reading, right? And then runtime NDNS handling is not supported by the project yet, but I'm planning to do this. But as of now, let's stick to compile time handle. And it should work with any streams like span streams, file streams, even maybe, I'm not sure, maybe regular input output stream, and also anything which the developer wants to use with, right? And this is what the promise looks like. The promise code is what the important parts are highlighted. So we are interested only in declaring the layout and then a single API call. It looks similar to your static cast. So we are casting a stream into a struct. So I chose the name struct cast in this case. And then we would have to do error handling. So the API would return you as did expected, and then you can either do your monadic operations or however you want to handle the error. So let's deep dive like how to do this in a very, very, very simple way. So that being said, a fair warning, template metaprogramming ahead. I've had a love-hate relationship with template metaprogramming, right? I mean, when I started working, I used to do, because I was fascinated by all the language features, and that's what every beginner would do. I wrote a lot of this, and then compile times blew up, and people were not happy about it. And whenever I write template type name ... I get faces. It's not angry faces, but they're not happy faces either. But I get the sentiment here. It's hard to get it right. It's a bit. It's too. I would say not pleasant to read, and you'll have to depend a lot on functional programming, and obviously they have slower compile times. But TMP has its own place, like our project here, like our little project here, where you want to generate something really at compile time by the compiler, also with strong typing and so on. So before we dive into the implementation, I want to give a little, let's say, some primer materials. Right, I have found this little 2 talks online. There are so many other talks also, but these 2 were really useful for me personally. They would teach you about template metaprogramming, and this I believe is like somewhat closer to intermediate level talk what I'm giving now. So I don't want to like explain all the terms about template metaprogramming, but I can direct you to a good material. So in this case, the first talk is by Mirok Nep. It's from CPP North. It explains how CTAD, non-type template parameters, and variadic templates work. And then there is this compile time functional programming, really good talk by Bartosz Milewski, where he explains about meta functions and how they are written in C++, right? But I would outline how these concepts are used in the project. That's something I would definitely cover going forward. Okay, now what are we building? So we are building only 2 of the use cases here. We don't want to cover all the stuffs I mentioned about earlier. That would take multiple talks to cover. But we would cover with our implementation in this talk for 2 use cases. One is your regular structs where you know the sizes of all the fields ahead, which means also including nested structs. And then there is one length prefixed string or vector in your struct. And then unfortunately you wouldn't get a normal member access because we are not generating structs here, right? Though I name them as struct field list or struct, we are not really creating a struct here at compile time. We are just creating a meta struct here with a layout, right, which we describe in this DSL. So we would only get a map-like interface. So if you have a struct field list variable, and then you will have to use a map square bracket operator to access your fields inside it. So let's start start building up ground up, like bottom up. So what would it take to describe this field, right? We have a field which is denoted by its name, its type, what is the type of the variable, and also what is the size we would like to read from the binary for this particular field. So the name itself is a string, right? You have to denote it as a string. But so far, at least until C++17, it's not possible to have strings in the template arguments, and it only supported very primitive, I believe, basic types only to be in the template parameter. If you want to use a non-type template parameter, but starting from C++20, we have the fixed string hack, right? Because it supports non-type template parameters, so you could pass in structural types as your template parameters. So in this case, I declare a template struct with size as its template parameter. I have a value member which is of type std array, and then we have it is array of characters, and the length is n+1. Why n+1? We want the null terminator for the string, and then we have two constructors. One is default, and the other one would just take like a constant array, character array, and then copy it into the member. And then some utility members, these are similar to your std arrays members, right? We want the data member, we want the size member. And additionally, I have the two string view to convert our fixed string into a string view. And then you can do all the operations of a string view. Let's say comparison, sorting, if you want to have with algorithms, and all the regular operations what you could have with a string view. And the next hack is the class template the CTAD, the class template argument reduction. So we can say if you provide me an array of n characters, the return type of the constructor would be a fixed string of n-1 characters. This way, you don't have to always provide this template parameter in few cases, right? And then we have obviously a comparison operator, because we want to make sure this is unique if you want to use somewhere. Now this should be possible. So you can pass in a sample with the hello as a template parameter. Now let's denote size. How do we denote a size? I have a field size. Again, it's a template struct, and then it can either take a fixed or a length from field, right? And a fixed is like your trivials, right? You can have integers, your floats, which would have a fixed length, but then you might want sometime to have a length hint. You might have to provide a length hint and say the length of my current field depends upon another field which is to the left of me, which you have already parsed. And the magic of field accessor is something I explain in the upcoming slides. So now we can denote a name, a size, and the type. So with those contraptions we built, we already have the field now. So a field is again a structure. It would take a template parameter as the ID. It's again a string, and then we have the type of the field, and then the size of the field, and then we have the value member, which is again the field type. So we are now able to denote our first field. And then this is also good because you could also put as another struct field inside this. You also get it for free because it's another type. You can just put it inside your field. Now we move to about how we explain our layouts. Like we have to explain the compiler, the layout. How does the struct has the fields inside it, right? So let's now maybe start building the field list. So we need a small utility to create a list of types. Like in C++, it's possible to have a list or a vector of objects at runtime, but how would you create a list of types? One way is to use a variadic template like this, and we can call it type list. and you can instantiate it with any number of types as a template argument. And then you can write a few meta functions with which you can manipulate the type list. You can say, okay, you can sort the types by sizes or sort it by alignment. Or you can say, what is the head of this list? What is the tail of this list? Or you can say, okay, I want to search something in this list. So this is possible with this small, really small. It's small, but it's really powerful. Then we need a literal for accessing our fields. Like I said earlier, we don't have normal member access, so we will have to somehow access these fields with a square bracket operator. But we need to build this small contraption because you can't directly use a string as an argument to this square bracket operator. The reason being, if you pass this, for example, I wouldn't be able to validate if this is really in our struct field list or not. If this given field you are requesting for, is it in the struct field list or not? And I have to use concepts to do some constraints here, and you can't apply constraints on function parameters. You could only do it on types, right? So I have to build this small little contraption which is called field accessor, and it would have the member field ID, and then the user defined literal operator underscore f, which would return this field accessor. So with that, once our field list, when it supports the square bracket operator, we can pass this as an argument. So now let's build a struct. Let's ramp up. So we have a variable template, for which we have two little concept constraints, C++20 concept constraints, which would ensure our fields are unique, right? And then if your field X depends upon a field Y, we make sure all such fields are occurring to the left of the fields, right? Because once if you would know the size only if you have already parsed it in this case. So we should make sure if a field depends upon another field, we should make sure it is on strictly to the left. So these are ensured by these two concepts, and failing to do so would result in a compiler error saying that the constraints are not satisfied. And then we create the struct field list itself, where I inherit from each of these fields. And one thing we should know that we had no rituals here. So what we can now write like a square bracket operator. In the square bracket operator, I'm passing in a field accessor as a parameter. So now I can write a small meta function called field lookup, which would look up for this field in the type list. So I create a list of fields as in like using this utility we saw in few slides earlier, and then I pass these two arguments to the field lookup, and this would either return me the actual field, the type we are looking up for, the complete field, or a sentinel called field lookup failed. And then we have a concept constraint again to say if this field lookup failed or not. If it failed, then in that case, at compile time, if you try to access a field, you would get an error saying again, constraint not satisfied. But how does the operator itself is working? So now we have got the field, right? The actual individual field we are looking for. If we static cast the complete struct field to this field, since we are not having any virtuals and we have all the fields have been inherited, we would do an object slicing, and this would result in only the field. And then we return the value member from that field alone. What we see now is a non-const version. You can also write a const version where you don't want to mutate the field. I mean the value inside the field. But how are the uniqueness and the dependencies are guaranteed? I have to do a bit of hand waving here, unfortunately, because these two meta functions would like to demonstrate them, it would take a complete talk. But again, these are meta functions. I do show a few more meta functions in future slides, how to write them. So in principle, anybody can learn based on that. But the basic concept is like we should make sure there are no repetition in the field names, because it's a struct. It's similar to your the other structs we have in the C++ language itself. We can't have duplicate and members in it. And then we also make sure the dependencies are always strictly to the left for each field which has a dependency. how does the lookup work like, right? I mean, I had this little meta function called lookup, right? Let's break down and see how to write a meta function in this case. So I have a sentinel called field lookup failed. It's an empty type. You don't have to worry about that. It's just a way to denote that our lookup failed. I have a field lookup, which would take either it will take one list and the ID to be searched for in this list, a field name matching this ID. And then and then we use template specializations to write our meta functions. So the first function is the base case of your recursion. In this case, if the type list is empty, but you're still looking for something, then we fail. We went to we scanned through the complete list of the fields, but we didn't find the field we are looking for. Or the success case. Here we pass in a field ID, and then we also have the actual field matching now in this instantiation of the template. In this case, we say, okay, yeah, I found the field. So I'm having a little type here using type alias, which would capture that field to have a result returned to the user. Or you have not found it yet, but you still have something in the type list. So we just keep going on. We instantiate the remaining of the templates. And the user exposed meta API would look like field lookup v, which would take the type member for type using alias inside our struct, the struct we defined. So this is how someone would write a meta function. This is an example, and then the same principle can be extended to look to making sure that the fields are unique or all the dependencies are met. How does the accessor work here? So like I explained already, it's like the static cast the hack, right? We have multiple fields and the struct is inherited from multiple fields. And then when we cast it, we do the object slicing. This is one of the places where object slicing is useful for us. And then we return the reference to the value inside the field. But in case if you don't have it, you would get an error like this. You would get there is no viable overloaded operator for the struct field list, and then the place where you try to access the field. But the best part is there is no pages of template metaprogramming errors, but rather a simple error saying that the field lookup failed and the constraint is failed. I know that this is not the prettiest error message out there, but this would get better in going forward with every standards. And in fact, the Clang does an even better job. I believe this error message is from GCC, if I'm not wrong, but I believe even Clang does a better job in this error messages. So now we can denote our layouts. So the layouts are done. We know how to denote an individual field, and we know how to denote a group of fields now. So next, let's start with the actual reading process. But again, we need some sort of utilities. So if you remember, to read something from a stream, we'll have to do we have to pass the character, the character star or version of the address of that object, right? So now I create a small byte address of, and there will be multiple overloads. For example, for any trivial type, we return just the address casted to char star, and for string it would be the first character of the string, and we can have multiple other overloads like for std array, for std vector, and so on. And it should be noted that reinterpret cast cannot be in const expr. It's not allowed to be in const expr, so these functions would not be in const expr. So the little version of this demonstration would not be fully const expr, but the implementation, the final implementation in the project, it is indeed const expr compatible. Then we need to reduce sizes, right, for each of this field. Again, I use some template hacks here. So this one is again some specializations of the template. So I have a reduce field size. So the first specialization here would take a regular field for which the size is known. Maybe it's an integer or so it's a float. In this case, we just return n because the pattern matching just works. When you instantiate this template with this particular field alone, then you would get the n out of it when you invoke it in the runtime, the operator when it's invoked at the runtime. And similarly, if it is a std vector, but then if you had an accessor mentioned, then this would be the second specialization. In this case, I would return the length times the size of the actual type held in the vector, right? That would be the number of bytes we'll have to read. And similarly, at the end, we have the string, which is like the size is known. The size of each member in the string is 1 byte. So I just return the return the value held by this member, which is which this string is dependent on for the field, right? The most important parts is to have errors, like readable errors. So I create an error reason, but for now I just have one member in this. In the error reason, it's buffer exhaustion. But you can have multiple errors, right? You could say, okay, if the validation failed, or I couldn't reduce the type for this field, and so on. But for now, in our little example, we just focus on the buffer exhaustion. And then a small little readable cast error, which is the error reason, and it also says at which field we failed while we were reading. I have one small type called read result, which is like a state expected of void and the cast error, but this is the result of just one reading one field alone, not the complete result, but just reading the result of one field, one single field. Then I write a small monadic pipeline. So this pipeline is a utility to handle our errors while reading multiple fields. So if you have n nodes in this pipeline, so each node would take a callable which returns a read result because it was reading a single field, and then each node does a simple operation. It's like it in an abstract sense. It can be imagined like it takes a box, and in this case, it's a state expected, looks inside a box, and if it checks if it is a value or an error. If it is a value, then we call the next callable in the pipeline. Else, we just short circuit by returning an error because the pipeline would just propagate the error alone after that. So this way we can read read it in a pipeline manner, which is easier to read, right? It's also a bit intuitive to imagine. And then we read at last. I have an implementation. This is not the user-facing API. It is just the implementation of the cast itself. So I have the struct cast to which we can instantiate with the actual type of struct we are trying to read, and also the stream. So I have made it like a generic for the stream because you can also extend this for any type of stream. As long as it is having the characteristics of an input stream, we can even add a concept here and constrain that, hey, it has to have a read method and it has to be convertible to bool, for example, right? So to avoid repeating and to keep things a bit cleaner, I have some aliases. Just alias. The first one is just I'm just copying out the struct into an alias, but the second one is the actual result we are returning to the user. The result would be either the struct or a cast error, right? It's again a box we're returning back to the user. We have a call operator, which takes a stream by reference. We create a field list as a local variable, and then we create a pipeline seed. Why we need this? Because you have to somehow jumpstart the pipeline, right? We have to assume initially the callable passed. So I say, okay, everything was okay. So I just put in a seed into the pipeline, and I just start triggering the process. And then we have the actual pipeline. So in this case, I have multiple callables, each reading just one field. In this case, I write a fold expression, and then this would like expand each of the fields from left to right in the same order we want to see this in the actual binary. And then each of the callables will be triggered if the previous callable has passed, right? And inside the callable, we do a little magic. The first step is to just extract the field out of the field list, and then we do operation on the field. But then at the end, if everything went well, if we check the result, if it is okay, then we return the field itself, or we return the error. So what does the magic look like? What is the magic we did in the lambda? So I have a little meta function. We have a field with multiple template parameters, and then I extract only the type out of it. And in an if context of branch, I check if it is a field list like is it a nested struct in this case? If yes, then recursively call struct in the public user-facing API. Else, if some, then when we take the return value and check if it is has it worked well. If not, then I return an error. and this would propagate because this is like a recursive function call, right? It will go down the stack, and the error would be propagated all the way up to where it was invoked. Or in then another if context per branch, I check if it is either constant sized or variable sized to make the the pattern matching complete. And then I use the deduce field size, which we wrote in a few slides ago, to deduce the field size. If it is variable size buffer, again, then I resize it, else I don't. And then I do a regular read from the stream because we know the byte address, we know the read size. If it passed, okay, it's fine. Else we return as like instead unexpected in this case. So how does the user API look like? So far everything is implementation detail. We don't want to put all this into the user code, and we don't want to clutter it. We don't want to bother them with all the implementation details. So there is one simple user-facing API. It's called field list like, and then also two concepts: field list like and input stream like, which would constrain the T and S, and then this is what makes user to just call a single struct cast in the user code, which we saw in the promise slide. And finally, I have some field descriptors. This is also some user-facing meta APIs. We don't want users to. We want to make users' life as easy as possible. We want to make sure that, for example, they don't try to read 6 bytes into a UN32 variable, because then we'll have to warn them ahead of time that they are trying to do something wrong. And then we don't want user to every time calculate the complete size and the number of bytes for the array they are trying to read from. So rather we can just get the length from the user, and we can compute in the library the number of bytes we'll have to read. Right? This way we also avoid a lot of human errors. So we have the field descriptors, we have the data layout, we have the cast API, and the implementation for that. So we have reached the promise. So this is the little version of the implementation. So there is also a link to the little version of the implementation here. What about benchmarks? Unfortunately, I didn't manage to create this. It was really difficult for me to compare here because I didn't have a reference for like a baseline for the comparison here. It would definitely be slower than a handwritten individually a hand-rolled written parser, right? It would definitely be slower because it's using a lot of templates, and I can't compare it with the solutions from the other languages. Then it would be apple to oranges. I couldn't do this, but I'm trying to do a reasonable benchmark here. But so maybe the slides, when the final slides are published, I would have something here. Else, I would update the GitHub, so, and people would have some measures like saying how fast it compiles, does it run as fast as the handwritten version, and so on, even in the runtime. Okay, but we are not quite done, right? You remember the little surprise I was talking about at the first? It's a reflection. So C++26 and the future standards are promising us reflection, static reflection, in where you can introspect the code at the compile time and then maybe even manipulate the types to a little extent. I believe that we don't have a full-fledged generation of code at compile time yet, but it also there is a paper for annotation for reflections where you can annotate your types. Where I have a little example here, but it's not related to the project itself, but I was trying to play around with annotations, and I have some GitHub link here. But with reflection, you would be able to do something what Rust does today. And nowadays, there is at least one talk which would talk about Rust in our C++ conference. Yeah, so here it is. So we have binrw crate, which is equivalent to a little project here, but Rust uses proc macros to do this, right? They have something called proc macros where you can annotate structures or variables, and then at compile time, the compiler would pass the execution and then take the tokens and pass it into a function you've written, and then you can manipulate the tokens and inject it back into the AST. So it also supports code generation already, but C++26 is yet to support it. It only supports introspection and these annotations. But we still have template metaprogramming, right? So you could still do all the annotations, make the user code clean and neat, but then underneath you can use template metaprogramming to generate your functions, right? And that is one of the main reason I chose to do this with template metaprogramming, because it is somewhat compatible with reflection proposals. And in fact, all my implementation in the GitHub are like using APIs similar to the reflection proposal. So in near future, this is possible. You can have a little annotation for your structs, and then the user-facing APIs will still remain the same. But yes, it's a partially breaking change for the layouts, where how you describe the layouts. But it's good. It's for the greater good because it's much more readable. But it's still possible to have normal member access because they are regular structs after that, right? But I retain the square bracket operator because this would be backward compatible. So this way we strive for backward compatible. So I'll leave it backward compatible this way. I plan to also complete this implementation, let's say by 2026, somewhere in 2026. Let's see how it goes. So finally, here is the link to the project. I have a link to the project, the complete version of the project. And yes, so don't be afraid to do projects. As a closing note, don't be afraid to do projects. You might fail. Maybe your project will become outdated because C++ supports reflection. But it's fun. It's fun. So you would learn a lot. You would meet a lot of people. You can crash compilers. You can crash your text editors. It's fun to do little projects when you're free. But it takes a village to do a project. So I would be happy to collaborate and extend the project. And these are the handles. And yeah, you can reach out to me in these handles. And I'll be happy to answer your questions also. So thank you.
Yes, thank you for your talk. That was an interesting presentation on binary parsing. And I think we're all looking forward to having the reflection with 26. This looks really nice. We have a little bit of time, so let me see if there's any questions. But anyways, you should be able at the conference to find Hari on the previous talk table and talk about his talk there. So thanks for coming and giving us a great talk. And
thank you. Thank you for having me.
There is actually a question which we could still quickly go into the stream for. So what would you change to make it runtime configurable?
I'm not clear about the question by what is runtime configurable. The layouts, you mean, or the question is not completely clear to me, unfortunately.
Yeah, I think that you could like have some sort of factory producing different parsers for different versions, but of course, what is created at compile time is not configurable by runtime.
Okay. But it's usually the case where the project is usually the case where we know the layouts up front, like for file formats, for example. And if we would like to choose the layouts at runtime, usually this would be based on some payload in something baked into the binary, right? If you to switch between two versions of the file formats, I'm sure most cases would have some sort of multiplexer at the front, and then you can also design this as part of your layout, and then make it a variant, like a variant. You can read either this or that. That's one way I understood, if I understood the question correctly.
Yeah. And I think that's like the classic serialization strategy is just to, have an enum for all the types you serialize, and then you write this enum value, and then you know what to read. And
like a metadata, you need some sort of a metadata there, because without that, because the types this is something how I imagine, like the types on the wire is not same as the types on the actual C++, right? So you need somehow to also denote the additionally these configurations with an additional metadata at the top, and then the parser can actually interpret it based on the metadata it read.
And there's of course always a option to use JSON when you need something human readable, but if you need performance of that format, is not discoverable as an alternative. JSON or XML are not.
Never XML. JSON is far better.
Well, you don't always get to choose. I know the comments when I write about handling CSV files, and people are like, why do you choose it? And I'm like, yeah, I didn't choose it, but it's just like a lot of sources choose to provide that format either.
Yep.
Anyways, thank you for your talk. And then to the audience at the conference, if you have any questions, I guess you already had the joy to have Hari in the chat. And then there will be the lounge ready to take on questions. Thank you, Hari.
Thank you. See you all.